Now we are seeing the another technique, that is your local search technique. Local search is a particular way of solving a CSP. Now we all know what is CSP, that is your constant satisfaction problem, and we are using local search technique for solving those problem. It keeps improving the values until all the constraints are satisfied. It iteratively keeps updating the variables until we arrive at the destination. Now in this, we are using iterations for updating our variable. These algorithms modify the value during each step of the process that gets us closer to the goal. So basically, in that algorithm, in our each step of the iteration, we are updating our variables and finally we are reaching our goal. In the solution space, the updated value is closer to the goal than the previous value, and hence it is known as local search. In that, in each iteration, we are updating our value, and that updated value will be closer to the goal. And if it is closer to the goal, then we will keep that updated value, and in this way we can finally get the output. Now what is that technique? It is a heuristic search algorithm. Now it is a type of heuristic search. These algorithms use a function that calculate the quality of each update. Now heuristic search algorithm will use a function. We are basically defining a function on that, which is actually calculating the quality of each update. Now what is the quality of each update? So let's say an example. It can count the number of constants that are being violated by the current update. So basically in each iteration, if you are updating a variable, then it will count the number of constants that are being violated by those current update. Or it can see how the update affect the distance to the goal. This is referred to as the cost of the assignment, and our overall goal will be to find the minimal cost update at each step. So basically we have to find out the minimal cost update. So let's say an example, hill climbing. Now this is a popular local search technique. It uses a heuristic function that measures the difference between the current state and the goal. So basically in that algorithm we are using a heuristic function, and we are defining that function which is actually measuring the difference between the current state and the goal. Now when we start, it checks if the state is the final goal, and if it is, then it will stop, and if it is not, then it select an update and generate a new state. If it's closer to the goal than the current state, then it makes it the current state, and if it is not, it will ignore it and continue the process until it check all possible update. So these are the following steps which will be followed in that algorithm. When we will start, it check if the state is the final goal, and if it is, then it will stop, and if it is not, then it will select an update and generate a new state. It will update its value, and if that update value is closer to the goal, then it will keep that update, and if it is not, then it will ignore that update. So basically we are also eliminating some options, and that's why we have used your heuristic function for that, which is the basic funda in heuristic function too, which is eliminating some options. So finally it will climb the hill until it reaches the summit. Simulated annealing. Now what is that? It is a type of local search as well as stochastic search technique. Now what is stochastic search technique? These are used in various fields such as robotics, chemistry, manufacturing, medicine, economics, and so on. We can perform things like optimizing the design of a robot, determining the timing strategies for automated control in factories, and planning traffic. It is a variation of the hill climbing technique. So one of the main problem of hill climbing is that it ends up climbing false foothills. Now what is the meaning of that? It means that it gets stuck in sometime local maxima. So it is better to check out the whole space before we make any climbing decision. In order to achieve this, the whole space is initially explored to see what it is like. This helps us avoid getting stuck in a plateau or local maxima. And that process is followed in simulated annealing, which is a variation of the hill climbing technique. So in that we will not get the problem, that is we are not ending up our climbing the false foothill. In simulated annealing, we reformulate the problem and solve it for minimization as opposed to maximization. So we are now descending into valleys as opposed to climbing hills. So in that technique, we are mainly reformulate our problem and solve it for the minimization and not for maximization. We are pretty much doing the same thing but in a different way. We use an objective function to guide the search, and this objective function will be served as our heuristic. So basically we have used here a heuristic function, and that's why it is a type of heuristic search technique. The rate at which we cool the system is called the annealing schedule. Now, we cool the system means we are descending our valleys. We are applying minimization, and that rate is known as annealing schedule. The rate of cooling is important because it directly impacts the final result. In the real world case of metals, if the rate of cooling is too fast, it ends up settling for the local maxima. If you are considering example of metal, then if the rate of cooling is too fast, then it will end up settling for the local maximum. For example, if you take the heated metal and put it in cold water, it ends up quickly settling for the suboptimal local maximum. So this is your real world example which is actually explaining the rate. So basically that rate is here annealing schedule, and we have to take care of it. If the rate of cooling is slow and controlled, we give the metal a chance to arrive at the globally optimum state. So if that rate is low and controlled, then we are giving our metal a chance to arrive at the globally optimum state. The chances of taking big steps quickly towards any particular hill are lower in this case. So since the rate of cooling is slow, it will take its time to choose the best state. We do something similar with data in our case. So that was your real world example, and the same thing we are following in our with our data in our case. We first evaluate the current state and see if it is the goal. If it is, then we stop. If not, then we see the best state variable to the current state. We then define our annealing schedule that control how quickly it descends into a valley. We compute the difference between the current state and the new state. If the new state is not better, then we make it the current state with a certain predefined probability. So basically these steps will be followed. So we are first evaluating our current state and see, we are checking if it is the goal. If it is, then it will stop. And if it is not, then we will update our variable. And then we are defining a schedule, annealing schedule that control how quickly it descends into a valley. That is, it is actually defining a rate that is related to metal. We compute the difference between the current state and the new state, then we are finding the difference, and if the new state is not better, then we make it the current state with a certain predefined probability. So we do this using a random number generator and making a decision based on a threshold. So we have followed all these steps using a random number generator and making a decision based on a threshold. So we are using a threshold for the comparison. If it is above the threshold, then we set the best state to this state. So we are using that threshold for the comparison. If it is above the threshold, then we will set our best state to this state. Based on this, we update the annealing schedule depending on the number of nodes, and we keep doing this until we arrive at the goal. Now based on that comparison, we will update our annealing schedule depending on the number of nodes, and finally we will arrive at the goal. So these were the steps which we have followed for finally computing our output. That is included your heuristic search technique, local search technique, because we are updating simulated annealing, and it is better than hill climbing, and you know very well what was the problem in hill climbing. So these were the steps which we have followed, and we have used all these process. So now let's see different examples in Python which are following those steps. Okay,